Hi, my name is Yuri Otov, and today I will be presenting my ICASSP 2022 paper, which is titled as Computationally Efficient Fixed Filter ANC for Speech based on long-term prediction for headphone applications. This is a research work in collaboration with Audio Analysis Lab, which is an Aalborg University, Denmark, and GN Audio company. So the outline of the presentation is the following. First, I will introduce what the problem is, then I will move to the multi-step speech prediction, then I will present the proposed method and following simulation results, and finally we'll make a conclusion. So lately, speech has become an increasingly unwanted source of noise and can be even more annoying than other types of noise. And the examples are very well known, such as working in an open office, or when nearby people talking on the phone, or when working or trying to concentrate in crowded public places, etc. Unfortunately, one major complaint from the market is that ANC headphones have quite limited performance canceling speech in such cases. In general, ANC systems can be based on an adaptive filter with filtered X LMS algorithm, for example, or based on a fixed filter. ANC in modern headphones is often based on a pre-calculated fixed filter for practical reasons like stability, computational complexity, and cost. The performance of an ANC system largely depends on several factors, and one of them is the causality of the ANC system. Figure 1 depicts a simplified modeling block diagram of feed-forward ANC headphones. So the causality constraint is violated when the signal propagation delay ADP of the primary pass is less than the electric EDS and acoustic ADS propagation delay in the secondary pass. And the optimal ANC filter in this case is non-causal, with the non-causal delay given as the following, which in general decrease ANC attenuation performance. So the region of the non-causal delay D, by example of ANC headphones, can be due to geometry problem, such that small size of headphones and short ADP can be due to contribution from EDS due to delays in the electronic components presented here, or due to direction of arrival of the noise, or due to improper headphone fit on the ear, etc. So the non-causal delay D brings a prediction problem into ANC system. And in adaptive ANC, adaptive filter acts as a predictor also to find a causal filter. While in case of causal feed-forward fixed filter ANC system, it will be unable to compensate for the occurrence of the non-causal delay D. So our focus is solving the prediction problem arising in a non-causal feed-forward fixed filter ANC system when the noise to be cancelled is speech. It is known that speech can be predicted, and a common approach for that is linear prediction. So we propose an integration of linear prediction into the ANC system to solve the problem by predicting the incoming disturbance speech D-samples ahead in time. We are focusing specifically on voice speech since it is the main constituent of speech and has much higher predictability than unvoiced speech. So the idea of the linear prediction that a speech sample X n plus 1 can be approximated as a linear combination of past samples. As was reported in previous studies, in order to maximize performance and reduce computational cost, the prediction order must include at least one pitch period, T, and only the first 8 to 10 coefficients, and those at the pitch period have a strong contribution to prediction performance. And this scheme represents the idea of combining a short-term predictor with a long-term linear predictor. However, linear predictor typically considers prediction by only one sample ahead in time, but for our purpose, multi-step linear prediction is required, meaning that we need to predict these samples ahead in time. And this can be obtained from the standard form of long-term linear prediction as the following, whereas on the left is short-term predictor, and on the right is long-term predictor. with M and Q being the prediction orders and prediction coefficients A and BK found jointly by minimizing the estimation error in the equation 2 in the mean square sense by, for example, normalized LMS algorithm. However, the above was reported for the classical linear prediction, so predicting only one sample ahead in time. And then there is a question, will it apply for the multi-step linear predictor, predicting these samples ahead in time? The following experiment investigates this. The prediction gain expressed in equation 3 is widely used as a prediction performance metric. And as can be seen, the lower the prediction error is, which is the difference between the original signal and the predicted signal, the higher the prediction gain is and the better the predictor is. So figure 2 represents mean prediction gain of voiced parts for multi-step prediction D by short-term predictor and long-term predictor as a function of long-term prediction order Q. On y-axis, there is mean prediction gain as a performance metric in dB. So focusing on long-term prediction order of 5, we can see that in case of the classical linear prediction, predicting one sample ahead in time, having only a long-term predictor, the performance is about 8 dB. But then combining it with a short-term predictor of order 10, we can see that there is quite noticeable performance improvement from 8 to 12 decibels. But then for the multi-step linear prediction, predicting 5 and 15 samples ahead in time, we can see that introducing a short-term predictor to the long-term predictor, we don't have quite noticeable performance improvement, and sometimes short-term prediction can even reduce prediction gain. So we can conclude that short-term prediction and long-term prediction scheme works for the classical linear predictor, while for multi-step linear prediction, long-term predictor is preferred since short-term predictor can reduce prediction gain and lead to higher computational complexity. Therefore, we propose to use a long-term predictor alone with the order of 5 as a prediction performance computational complexity trade-off. So for the proposed method, first we are going to analyze the effect of the non-causal delay D on residual ANC error in the Z transform. Firstly, for causal feed-forward fixed filter ANC with optimal filter W, the residual error is 0, leading to a perfect cancellation. However, perfect cancellation may be not realizable in practice. So the optimal filter W can only be realized if S of Z is a minimum phase and stable and causal inverse exist. So the fixed filter W is based on a priori calculation using pre-measured primary and secondary paths. So ANC performance of this system will depend to a great extent on the accuracy of the measured P and S and their stationarity. The second case for the same feed-forward fixed filter ANC system with filter W and non-causal delay D. Here we have an assumption that the non-causal secondary path S of D consists of minimum phase S of Z and a pure delay Z minus D. And as can be seen from equation 6, the ANC performance will depend on the amount of pure delay D in this case, and in general, ANC performance in this case will be significantly decreased. So in the proposed feed-forward fixed filter ANC system, the issue of a non-causal delay D is solved by integrating the long-term linear predictor filter into the ANC system. In this case, the ANC performance of the system, as can be seen from equation 7, will depend on prediction performance, such that the accuracy of the predicted signal compared to the original signal. And if this difference is close to zero, then the ANC performance is higher. So in order to verify the above, the following slides presents simulation results, specifically speech attenuation performance of the proposed feed-forward fixed filter ANC with non-causal delay D and integrated long-term predictor in comparison to the adaptive filter text and LMS ANC system and feed-forward fixed filter ANC without long-term predictor. And there are some simulation conditions. So all filter orders found based on the empirical simulations with performance computational complexity trade-off, primary, secondary, and estimation of the secondary path were simulated as bandpass minimum phase filters with the following frequency ranges. And the estimation of the pitch period for the long-term predictor was performed based on the fast fundamental frequency estimation on a sample-by-sample basis. So figure 3 represents simulations of mean attenuation gain of voice speech as a function of non-causal delay D. It is average over 12 male and female speech signals. On the y-axis, there is a mean attenuation gain, which is used as a performance metric. The higher the attenuation gain value, the better the performance is. So firstly, let's consider the case of fixed filter ANC system without delay or with an ideal predictor. In this case, the system reaches about 28 dB of mean attenuation gain. And looking at the plot of the bottom, we can see the effect of the non-causal delay when the performance drops from 28 dB to, let's say, minus 3 dB of attenuation gain, which leads to noise amplification. And then for the proposed system, we can see that there is quite noticeable performance improvement by integrating long-term predictor. So the benefits of the proposed ANC system that it reaches comparable or better mean attenuation gain than the adaptive filter DEX and LMS ANC system presented in blue at a wide range of the non-causal delay, specifically from 4 to 18 samples, which corresponds to 0.5 to 225 milliseconds at a phase of 8 kilohertz. At the same time, the computational complexity is reduced in terms of number of multiplications, additions, and divisions, which can be seen from the corresponding table. And the higher the prediction gain, the higher the attenuation gain, which can be seen that the proposed system attenuation performance is linked to the prediction performance of the long-term predictor. So as conclusions, firstly, for multi-step voice speech prediction, long-term predictor is a preferable choice in terms of performance and computational complexity trade-off. Then the proposed ANC system reaches comparable or better mean attenuation gain of voice speech than the conventional filter text and LMS ANC system at non-causal delays from 4 samples, while reducing the computational complexity. The mean attenuation gain of voice speech is an average of 8 dB for the proposed system. And then for the proposed feed-forward fixed filter ANC, the higher the prediction gain, the higher the attenuation gain. And for the future work, we can think of focusing on a more effective prediction scheme with a higher prediction gain, which will lead to a better ANC performance of the proposed system, then investigating different integration structures of prediction to improve ANC system efficiency, and also investigating how the unvoiced part of speech can be processed along with the voiced part, and finally conducting real-time experiments. Thank you for your attention, and you are welcome to ask me any questions.